The problems that we're going to do in this segment involve nth roots. On the right side, I've included a spreadsheet that shows the perfect squares, perfect cubes, perfect, I guess you could say, fourths, and perfect fifths. These are also ones that you should know by in the top of your head with memory. Therefore, the problems that I plan on doing, you should never need to go to a calculator. For example, if I'm asking you what is 49 raised to the 1/2, what I'm really asking you is, what is the principal root of the square root of 49? If I go to my chart, I look at my chart, I see that 49 here is listed under my x squareds. I come over to this cell, I say that equals 7. Again, remember, it will only give me the positive form of the answer if this is a even root. So if I was to ask another problem that said, for example, 81 raised to the 1/4, I really am asking the fourth root of 81. I can come over here to my chart. I can look at that the 81 is listed as my fourth root. I come over here to this cell. I see that the fourth root is going to come back as 3. If I was asked to find, let's say, the 343 raised to the 1/3, that would be the cube root of 343. One more time, I'll use my chart. I'll come over here to this cell, which is 343. It's under x cubed. I come over to and look at my x, and it tells me my value is 7. Now, if I chose to do negative numbers, for instance, if I decided to do what is the cube root of negative 343, I would get negative 7, because remember, negative 7 times negative 7 times negative 7 would work out to be negative 343. The problem is, if I do any of these problems here, specifically the negative 49 raised to the 1/2, and it really won't be any different if I do negative 81 to the 1/4, I'm really asking is, what is the square root of negative 49? And the square root of negative 49 for real numbers would be something that does not exist or not part of our real solution, because you would think that maybe the answer should be negative 7, but a negative 7 times a negative 7 still works out to be a positive 49, so that isn't a square root of negative 49. If I want negative 7 to come out, what I would need to have done is either write the negative in front of the parentheses, and to be honest, I don't even need to do that. I could write it just as negative 49 to the 1/2, because by please excuse my dear Aunt Sally, the exponent would get done first, and it would come back as negative 7, because this would be done first, and then the negative would come second. Now, as we go a little farther, we can start doing some more challenging problems. For instance, let's take a value of 27, and we will raise it to the 4/3. Well, first thing is I'm going to realize is 27 is a number I should recognize, and I recognize as a cube root. Luckily for me, 4/3 is really nothing more than 1/3 times 4. Well, by using my exponent rules, I could do 27 to the 1/3 first, which actually means do the cube root of 27, take that result and raise it to the 4th. Well, due to the fact that cube root of 27 is 3, and 3 then is raised to the 4th, I would get an answer of 81, never have to touch my calculator. Same thing with some of these other problems. For instance, if I asked you to do 1/64, and I asked you to, let's say, raise that to the 1/2, I could use my exponent rules and realize what I'm really asking for is 1 to the 1/2 and 64 to the 1/2. Well, 1 to the 1/2 is really the square root of 1, which is 1 for the numerator. 64 to the 1/2 would be square root of 64, which is 8, and I could get an answer of 1/8. It could be even more interesting if I would have had, let's say, a fraction 32 over 243, and we'll raise that to, let's say, the 2/5. What I'm really going to need is to look at my chart, which hopefully now you're beginning to realize the numbers that I am choosing now, I want you to do without a calculator so that you can practice these skills. So therefore, if I come back to my spreadsheet, you'll see that 32 is listed under the x to the 5th column, and so is 243, which is good because I come back over here to this side and I realize technically this could be written as 32 to 243 raised to the 1/5. Take that result, square it. Now I just have to realize what is the 5th root of 32. What is the 5th root of 243? Whatever those numbers are, I'll square them. If I go back to my chart here, oops, let's try that. 32, 243, those numbers would be 2 and 3 when I take the 5th roots of them. So I will get 2/3. I'll square it, and then I'll come up with 4/9 as my final answer. 17, and I raise it to the -2. What that really means is for a negative exponent is to go 1 over 17 squared. Since that is a squared, I can actually use the chart over here on the side in reverse. Realize that if I look at 17 and I look under x squared, that would be the same as 289, therefore 1 over 289. Now, if I want to start getting a little bit more involved with fractions and also negative exponents, I might take a chance at doing 512, dividing that by 729, and raising this to the -2/3. One of the keys to doing this problem is remembering that a negative exponent means everything actually gets placed into the denominator, and then raising it to the 2/3. Well, I have a slightly different approach. Since 512 is going to end up being in the denominator, and 729 eventually is going to come to the numerator because we will be multiplying by the reciprocal, I personally think it's easier to write 729 over 512 first. Now, instead of talking about a -2/3, talk about a +2/3. Now I can take the cube root of 729 and divide that by the cube root of 512. This, of course, would be 9. This would be 8. Each of these, technically, are all squared, because I was never done, and I can come up with 81/64 and have an answer without ever touching a calculator, and more importantly, having an exact answer. A couple more problems I'd like to go over is quantities. For instance, if you have a to the 3rd, b to the 4th, c to the 5th, and you raise it to the 6th, just remember that each one of these pieces, a to the 3rd, could be raised to the 6th, b to the 4th could be raised to the 6th, c to the 5th could be raised to the 6th, and you would come up with a, and using the exponent rules, you multiply 3 and 6 together, you get 18. B, you multiply the exponents together, you get 24. C, you multiply the exponents together, you get 30. Sometimes we can make a problem look more entertaining just by adding some radicals with it. For an example, if I have d raised to the 5, I have e raised to the radical 5, and I have f raised to, let's say, 2 radical 5, and then I decide to raise the whole thing to a radical 5, you're going to have to remember all the different rules involving the radicals. For instance, I still need to apply d to the 5th and raise it to the radical 5. If I'm going to multiply these together, because that's what powers of powers do, realize that this 5 here is outside the radical, this 5 is inside the radical. Therefore, if I'm going to multiply them together, all I'm going to be able to do is get d to the 5 radical 5. On the other hand, if I do this piece and I say e is raised to the radical 5, and then I raise this to the radical 5, I am allowed to take my two radicals, multiply them together, I'll do that work over here, and come up with radical 25, which means radical 25 could be rewritten as e to the 5th. If I'm going to do f to the 2 radical 5, and I raise it to the radical 5, I will multiply the exponents together. Well, 2 radical 5 times radical 5. Again, these pieces can be multiplied together if you're looking at what you can put in the inside, so that would be 2 radical 25, and 2 radical 25 would be the same as going 2 times 5, which means I can call this as f to the 10th. Therefore, my final answer would have been d to the 5 radical 5, e to the 5, f to the 10th. Watch out for certain problems where you might go g raised to the radical 7 times g raised to the 3 radical 7. Under these circumstances, a lot of students would think you want to multiply the radical 7s together, when in actuality what you do is you want to add them together. And if you add them together, that means you actually have 1 radical 7 plus 3 radical 7s, which means it will be g raised to the 4 radical 7. Again, I've mentioned this one on other occasions, that if you have hj, and let's say you raise it to the 4th, you're allowed to go h to the 4th, j to the 4th. If you have h squared j to the 3rd, and you raise it to the 4th, you can go h squared to the 4th, that's a 2, which means it's h to the 8th, and j cubed to the 4th, which is, times j to the 12th. So h to the 8th, j to the 12th. But if this problem would have been h plus j to the 4th, you are not allowed to multiply the h to the 4th and the j to the 4th. What this is really saying is you would have to go h plus j, h plus j, h plus j, and h plus j. And what your real answer would end up being is going to be h to the 4th plus 4h cubed j plus 6h squared j squared plus 4hj cubed plus j to the 4th, which would look nothing like what a lot of students would say. They would like to say it simply was h to the 4th plus j to the 4th. These two aren't even close, and that is just bad. So watch out when you're taking an expression that is adding or subtracting compared to multiplying. Just like if you had seen radicals. If you have a radical 7 and you multiply that by, let's say, radical 3, that would be the same as radical 21. If you have radical 7 plus radical 3, you've got radical 7 plus radical 3.